Alright, silly people, here's the situation. Uh, we're basically going to be doing the integral of this square root of 1 minus x squared function over dx, over the integral of minus 1 to 1, computationally, using the formula for the Riemann sum, right? So this is going to be nice because we know that the result is going to be pi halves, just given the fact that it's a semicircle and we're getting the area of it. Um, and since pi is such a precise number, we're going to be able to check for accuracy really well as well. So um, it's fairly straightforward. I see that there's a square root in the y sub k formula though, so I'm going to go ahead and import numpy so I can get that nice square root function. And so n is equal to 100 for the first part of the problem. Yeah, that's just in the part A problem statement to do the integral. And we know it's going to have to be a sum, so let's do a for loop then, for k in range, and we'll have it start at 1 and then go to n plus 1 so that you get n inclusive as per the formula there. It has to go all the way to n. And so inside the loop, we can calculate what h sub k is, and that involves the variable h. It's minus 1 plus hk, so I realize now that I should have a line outside the loop that says h is equal to n, or 2 divided by n is what it should be. It is pretty cool. Then we can do xk, which is h times k minus 1. And then same thing for yk. Now we can calculate that using numpy square root 1 minus xk squared. And then it's a sum, right? So we'll do I plus equals yk as we go. And that should take care of that. And then we can print the value of I. So very simply, after we run that, it'll give us, wow, okay. Didn't even run. I wonder what the problem is. Oh, it's because it wants me to define what I is, first of all. So I equals 0. And actually, I have to multiply this result by h. A couple of mistakes, but that's okay. We're doing this in real time. But yeah, that now it looks good. So 1.569 as compared to 1.57. It's fairly accurate. It can be more accurate though. Of course, it gets more accurate as you increase n, but we want to run it in like less than a second, according to problem like part B of the problem. On this computer, I got it to be around 680,000 for n, and still run in about a second. Let me try that real quick. So yeah, that executed in 1.238 seconds. I wonder if it'll run quicker if I do it again. That one, no, it actually went longer. But earlier it was 680,000 to get, and it ran like 1.01 seconds for me. And it prints out the correct value up to like 8 decimal places, I think that is. No, 7 decimal places. No, 8. Yeah, it printed out the correct value to 8 decimal places, which is really cool. Of course, if you increased it more, it would be more accurate, but it would take a lot more time. So there you go.